This is the Unit 4 review over optimization, Rolle's theorem, the mean value theorem, first and second derivative tests, and concavity. Start with number 1. Here we have to show that the function f of x, which is x squared minus 3x plus 2, satisfies Rolle's theorem on the interval 1 to 2, and then find the c value that is guaranteed by the theorem. To satisfy Rolle's theorem, the function must be continuous and differentiable. Because this is a parabola, simple quadratics, any polynomial is always going to be continuous and differentiable over any interval. If you want to show it for harder functions, you just need to prove that the derivative is continuous, it has no holes or asymptotes, and the function itself has no holes and asymptotes. Rolle's theorem itself says, well, f of a has to equal f of b. Plugging 1 into the function, we get 0. Plugging 2 into the function, we also get 0. So f of 1 does equal f of 2. And since the function is continuous and differentiable, it will satisfy Rolle's theorem. Rolle's theorem says that somewhere between the points 1 and 2, the slope of this function has to be 0. Well, we take the derivative to find out the slope of the function. It's 2x minus 3. When will 2x minus 3 equal 0? A little bit of algebra. At x equals 3/2. And there's our answer. In number 2, we are finding the value c, or all values c, on the interval from 2 to 7 that satisfy the mean value theorem for f of x equals 9 minus 14 over x. Well, the mean value theorem says that the slope of this function, as long as this function is continuous and differentiable, and this function is continuous and differentiable over the interval 2 to 7, there is an asymptote in this function. It stops existing when x equals 0, but that's not in our interval, so we don't have to worry about it. But the slope of this function must somewhere be equal to the average slope of the function over the interval 2 to 7. So we plug 2 into the function, and plugging in 2 gives us 2 out. That is just 9 minus 7 over 2, 14 over 2, which is 9 minus 7 or 2. And we plug 7 into the function, and that's going to be 9 minus 14 over 7, which is going to be 7. The average slope over the interval 2 to 7 then is found by 7 minus 2 divided by 7 minus 2, which is 1. The mean value theorem is somewhere between 2 and 7 on this function, the slope has to equal the average function, which is 1. So the slope of this function is given by the derivative. The derivative is 14 over x squared. If you've forgotten that part of derivatives, when you see negative 14 over x, you can rewrite it as negative 14x to the negative first power. And then the power rule works, and you get 14x to the negative second, which is simplified there. Okay, so the question is, when will 14 over x squared equal 1? That's going to happen when x squared equals 14. And x squared equals 14 when x is a positive or negative square root of 14. This, however, is not the correct answer, because the answer that satisfies the mean value theorem will be on the interval 2 to 7, which means we do not have to worry about the negative. It's strictly the positive square root of 14. And there's our answer. Moving right along number 4, it gives us the position function, s is equal to t squared minus 3t plus 8. And it wants to know the average velocity between 2 and 4. To find the average velocity, we need total distance over total time, which is again just a slope formula. So we plug 2 into the function and we get 6 out. We plug 4 into the function and we get 12 out. So that means at 2 seconds the object was at position 6, and at 4 seconds the object was at position 12. The distance over time then is found by 12 minus 6 divided by 4 minus 2. And that gives us an average velocity of 3. And that is not labeled. It should be whatever units the problem is working in, meters per second, miles per hour, whatever it is. Pushing on number 5. The exact same type of problem, except this time they want the instantaneous velocity. S is equal to t squared plus 9t minus 5. And they want to know the instantaneous rate of change at t equals 3. So for the instantaneous velocity, we take the derivative. S prime is 2t plus 9. S prime at 3 is going to be 2 times 3 plus 9. And so we get 15. Number 6, the position function, f of x, which is x squared minus 8x plus 11. And they're asking for the instantaneous rate of change of f. To find the instantaneous rate of change, that's the derivative. F prime of x is 2x minus 8. That is the entire thing. Number 7 is a little bit longer a problem. It's asking, or it's telling us, that the volume of cubic feet, in cubic feet, of water in a tank is equal to 2 times t minus 8 squared, where this is in cubic feet and time for the problems we measured in seconds. Part A. The average rate of change from 3 to t equals 5. We've done a few of these problems. We simply plug 3 into the function. We plug 3 in. We get 50. In other words, at 3 seconds, there are 50 gallons of water in the tank. And then we plug 5 in. At 5 seconds, there are 18 gallons of water in the tank. The average rate of change then between 3 seconds and 5 seconds is 18 minus 50 over 5 minus 3. That's going to be negative 32 over 2, which is negative 16 cubic feet per second. With all these answers, if you can, you should always verify that your sign is good. The negative appears correct because over time, the amount of water in the tank is definitely decreasing. Part B, don't worry about right now. We'll hit that when we review limits. Part C, the instantaneous rate of change at t equals 3. Well, we just have to take a derivative and then plug in 3. You can derive this with the chain rule. The 2 drops down to the front, giving you 4. T minus 8 times the inside derivative 1. And when we plug 3 in, we get negative 20. Lastly, part D. Part D says, what's the instantaneous rate of change at any time? Well, that's ironically, or coincidentally, exactly what we got in part C. Our instantaneous rate of change at any point in time is going to be 4 times t minus 8 times 1. Of course, when we simplify it, we will never write times 1 because that's silly. Moving along. Number 8. In number 8, we're finding the points of inflection on the curve f of x equals x cubed minus 12x. The moment you see point of inflection, you immediately drive to the second derivative. The first derivative, 3x squared minus 12, and the second derivative, 6x. That's it. The points of inflection will always occur when the second derivative equals 0 or doesn't exist. 6x will exist everywhere, so we're only worried about when it equals 0. And that only happens when x is 0. So this will have a point of inflection. If it has a point of inflection, it will only be at x equals 0. Let's verify that it actually is inflecting at 0. To do that, we take a number before 0, say negative 1, and we plug that into our second derivative. When we plug negative 1 into our second derivative, we get negative 6. That means the function is concave down when we're on the left side of 0. Then we go to the right side of 0, say we take 1, we plug that into our second derivative. 6 times 1 is 1, and that's positive. 6 times 1 is 6, and that's positive, which means the function is concave up on the right side of 0. If it's concave down on the left and concave up on the right, then it changed concavity at 0, and that means it is a point of inflection. This actually wants the entire point. Well, 0 is the x value. To find the y value, we take 0 and we plug it in to the original function. That's how we find our y values. And 0 cubed minus 12 times 0 is 0. So this function inflects right on the origin. Number 9 is a similar problem. We're finding the points of inflection of f of x equals x to the 4th plus 6x cubed minus 10. Since we're looking for points of inflection, we will head straight for the second derivative. The first derivative, 4x cubed plus 18x squared, and the second derivative, 12x squared plus 36x. We find points of inflection when our second derivative is equal to 0 or does not exist. To solve this, we can factor out a 12x. And x is equal to 0 or negative 3. We then verify that these are points of inflection, or either one is a point of inflection, by finding out whether or not the graph actually inflects there. When I plug in a number smaller than negative 3, and I'm going to plug it into the second derivative, okay, because when you're looking for points of inflection, we need to know if the concavity is actually changing, and concavity is a second derivative concept. So when I plug negative 4 into my second derivative, I get a positive number. Therefore, my graph is concave up to the left of 3. When I plug in negative 1, I get a negative number. So it's concave down when I'm right of negative 3. And when I plug in a positive number over here, I get a positive. Therefore, my graph is concave up, then concave down, then concave up again. My points of inflection will again be at or both these rather, are definitely points of inflection, -3 and 0. Those are just the x values. In this problem, we also want the y values. To find the y values, we take those and we plug them in. When we plug in 0, we get -10. When we plug in -3, we get -91. And that's it. In number 10, we're again finding the points of inflection. We have a pretty complicated function here in that 3x times x plus 2 cubed. In order to take the derivative, we are going to have to do a chain rule inside of a product rule. That seems gross to me, especially this late at night. So I'm going to opt to multiply this out algebraically and change the function, or at least the way the function looks, into 3x to the 4th plus 18x cubed plus 36x squared plus 24x. Alright, our first derivative. Notice up here I'm not taking the derivative. These two equations are exactly the same. One's just been multiplied out algebraically. You do risk making some simple math errors doing that, but it will make the rest of the problem much, much easier. So my first derivative is 12x cubed plus 54x squared plus 72x plus 24. And my second derivative is 36x squared plus 108x plus 72. We set the second derivative equal to 0. All of this is divisible by 36, which gives us a simple quadratic x squared plus 3x plus 2. To solve, that factors into x plus 2 times x minus 1, and our possible, x plus 1, sorry, and our possible points of inflection are going to be at -2 and -1. We plug points around those into our second derivative, and before -2, so say -3, plug that into my second derivative. When I plug -3 into my second derivative, I get a positive. When I plug -1.5 into my second derivative, I get a negative. And when I plug 0 into my second derivative, I again get a positive. So my function is concave up, then concave down, then concave up again, which means -2 and -1 are both points of inflection. To find the correlating y values, we simply plug -2 and -1 into the original function. When we plug in -1, we get -3, and -2 yields 0.